Let's talk classification algorithms, the backbone of so many data science projects. If you've ever wondered, how does a computer decide if this is a cat or a dog, or whether an email is spam? Classification models are the answer. Unlike regression, which predicts continuous values, classification is all about predicting discrete categories or classes. Picture it as the tech version of sorting your laundry into whites and colors, except, way smarter. First up, don't let the name throw you off. It's actually a classification algorithm, not a regression one. Here's how it works. Instead of fitting a straight line to your data, logistic regression applies a sigmoid function, which squashes any value into a range between 0 and 1. That output is the probability your data point belongs to the positive class. For example, say I'm building a spam filter. If the model spits out a 0.9 for an email, that means there's a 90% chance it's spam. Typically, if this probability is above 0.5 comma, the email gets flagged as spam. Up next, or SVMs. These are all about finding the optimal boundary, called a hyperplane, that separates classes of data. Imagine drawing a line on a 2D plot that perfectly splits cats from dogs. The support vectors are the closest data points to this line, and SVM tries to maximize the distance, or margin, between them. For data that isn't cleanly separable, SVM uses what's called the kernel trick, which basically transforms the data into a higher dimension where a straight separation becomes possible. Then there's OrganN. This one's super intuitive. It doesn't actually learn a model in the traditional sense, instead it just stores the training data. When a new data point comes in, KNN checks its K closest neighbors, say 5, and assigns the new point to the class that's most common among those neighbors. So, if 3 out of 5 neighbors are cats, the new data point is a cat. Choosing the right value for K is key. Too small and the model's noisy, too big and it might miss important details. Now how do I know if my classification model is actually good? That's where evaluation metrics come in. Accuracy's helpful, but it's not the whole story, especially if the classes are unbalanced. It breaks predictions into 4 buckets. True positives, true negatives, false positives, and false negatives. From this I can calculate the fraction of positive predictions that were actually correct. High precision is what you want if you can't afford false alarms, like a medical test for a rare disease. Next is, how many of the actual positives my model caught. This matters when missing the positive cases is costly, like fraud detection. The balance is precision and recall, giving a single number to summarize performance, especially useful for imbalanced data. And then, there's it plots the true positive rate against the false positive rate at various thresholds. The area under this curve, tells me how well my model can distinguish between classes. A perfect model gets an AUC of 1, a coin flip is 0.5. So, whether I'm building an email filter, a medical diagnostic tool, or a wildlife classifier, understanding these algorithms and metrics is crucial. Master these, and you'll be well on your way to acing your data science journey. Thanks for listening. Keep exploring, keep questioning, and keep learning.